In the late 1800s, physicists noticed a strange behavior in their laboratories. When they shined ultraviolet light onto certain metals, the metal surfaces would suddenly eject negatively charged particles. To figure out exactly what was happening, scientists couldn't just observe the metal out in the open. The ambient air is full of gas molecules that would immediately block or scatter those tiny ejected particles, making accurate measurements impossible. They needed complete isolation. To study this photoelectric effect, researchers had to build a specific, carefully engineered trap to capture and measure the raw interaction between light and matter. The setup's foundation is an evacuated glass tube, creating a vacuum for an unobstructed path. A quartz window allows high-energy UV rays to pass inside, striking the photosensitive emitter, labeled plate C. Directly across the gap is the collector, plate A, acting as a backstop. With the air removed and the plates locked in position, this vacuum chamber becomes a pristine arena, perfectly primed for a controlled collision between radiation and metal. The experiment begins with the light source, a beam of monochromatic light, meaning light restricted to a single specific color and frequency, is fired straight through the quartz window. The moment light strikes plate C, it transfers energy into the metal, violently ejecting electrons off the surface and into the empty space. But those loose electrons need a reason to cross the gap. To pull them over, the plates are wired to a battery, applying a positive charge to the collector plate. Because opposite charges attract, this voltage physically pulls the electrons across the vacuum until they hit plate A. By catching those electrons and funneling them into the external wire, the apparatus successfully translates an invisible microscopic collision into a continuous, measurable flow of electricity. To quantify that flow, a microammeter is spliced into the circuit. It measures the exact rate of moving electrons. Alongside it sits a voltmeter, measuring the exact electrical pressure the battery applies between the emitter and the collector. The critical control mechanism is the commutator, a specialized four-way switch between the battery and tube. Flipping it instantly reverses the polarity of the plates. Plate A becomes negatively charged, creating an electrical wall of repulsion that pushes back against the incoming electrons. By reading the total flow of electrons on the microammeter and slowly increasing that negative voltage until the flow stops completely, researchers can calculate the exact maximum kinetic energy of the ejected particles. You can think of this entire physical setup as a master control board. It gives the experimenter independent command over 4 specific variables. The first dial is intensity, which is adjusted by simply moving the light source closer or further away. The second is frequency, controlled by changing the color of the incoming light beam. The third dial is the potential difference, manipulated using the battery and the commutator. And the fourth is the material, adjusted by physically breaking the vacuum to swap out the type of metal used on the emitter plate. By holding 3 of these variables steady and systematically sliding the fourth, physicists could isolate exactly how light behaves when it hits solid matter. At the time, the accepted scientific consensus was that light traveled as a continuous wave. That classical wave theory made very specific, logical predictions about what should happen to the electrons when those 4 dials were adjusted. But the hard data produced by this exact setup contradicted the classical predictions. For instance, increasing the light's intensity didn't increase the energy of the electrons at all. And if the light's frequency was too low, 0 electrons were emitted, regardless of how intensely the light was shining. The results from the glass tube proved that light does not interact with matter as a slow, continuous wave. It hits as discrete, instantaneous packets of energy. The precise measurements pulled from this vacuum tube gave Albert Einstein the exact mathematical proof he needed to establish the concept of the photon, laying the physical foundation for the entire quantum revolution.